Would you believe that this massive building complex is meant to be a giant battery? The EVX is a project between the company Energy Vault and the Chinese government. It's the world's first gravity energy storage system, or GSS, built to store and release energy from the nearby wind farm. Gravity storage facilities are set to turn the world of energy storage upside down and provide a genuine alternative to the likes of Tesla's overly complicated lithium-ion megapack battery facilities, not to mention the controversy surrounding the mining of lithium and rare earth minerals needed for this tech. Built in the province of Rudong, the EVX is a 120m high facility that houses several blocks made of soil, sand, or recycled waste, each weighing 24 tons and around 12 cubic meters. The entire building is automated, hooked up to the power grid. An AI program reacts according to the power requirements of the moment, moving the blocks up and down using specialized lifts to store and release power as needed. The entire structure is capable of channeling 100 megawatt-hours per hour, with a peak power output of 25 megawatts. With its round-trip efficiency projected to be over 80% and an estimated 35-year operating life, it promises the power capacity and consistency needed to support China's extensive electrical grid. The project is a response to a growing problem. As the world pivots as fast as it can towards using renewable energy, what will happen when the sun isn't up, when the wind isn't blowing? With our power dependent on the whims of nature, will we just lose electricity when the conditions aren't optimal? Even managing power demand at peak times is likely to become a big issue. The increasing demand for EVs is threatening to put a heavy burden onto the grid. So much so, in fact, that companies are already looking to incentivize or automate off-peak charging. The AI boom looms heavy over the grid as well, promising even more stress with the amount of power they need. Just as the world rushes towards renewable energy sources, there's also a rush to find the energy storage capacity to keep electric output consistent, even if the sources are inconsistent. In short, we need batteries big enough to power entire cities for hours at a time. Enter the gravity battery. High school science class teaches us that still objects hold potential energy. Pushing the objects into motion transforms that energy into kinetic energy. This entire principle is what powers a gravity battery. The system can consist of multiple weights or a single huge one. When there is a surplus of electricity being generated by wind turbines and solar panels, a motor pulls the weight up. To lift an object, you need enough force to counter the gravity pushing it down over the height that the object needs to rise. That force, multiplied by the distance traveled, is work, or energy invested, in the object as gravitational potential energy. This stored energy is so handy because it doesn't degrade over time. A falling object still falls with the same energy it took to lift it. This makes it the perfect long-term energy storage. This is how gravity batteries release electricity during times of high demand. The weight falls, turning the motor into a generator. The movement turns potential energy into kinetic energy, which then turns into electricity. It's the same principle behind pumped hydroelectric storage facilities. Pump storage is a technology that's been around for over a century now. Its history can be traced back to Italy and Switzerland in the 1890s, where the concept was first researched and applied. However, it wasn't until 1907 that the first pump storage facility was built, the Ennua near Schaffhausen, Switzerland. This seemingly humble pond is still operating to this day, and with its refurbishment back in the early 1990s, is scheduled to keep operating until at least 2022. This just shows the power, resilience, and reliability of the pumped hydroelectric storage method. It requires an elevated body of water connected to a lower elevation reserve, with the main facility connecting them both. The elevated body of water is dammed up, waiting for the moment when more electricity is needed. When electricity is in high demand, the water is allowed to flow through turbines hooked up to the electric grid, turning the entire facility into one giant generator. Once there is less demand for electricity and during a period of lower electricity costs, the pump storage facility takes electricity from the grid instead. This powers the turbines to spin, drawing water back up from the lower reservoir to the more elevated one, storing up water and energy once again. The only energy loss concerns with pumped hydroelectric storage come from water evaporating from the reserve. The pumps or turbines are generally 90% efficient, so as a whole, pump storage operates very efficiently with only minor costs incurred by the whole cyclical process. The difference between pump storage and gravity batteries is that gravity batteries are marginally more accessible. Pump storage facilities require large elevated bodies of water and a reservoir at the bottom. Not every city, or even country, has access to a landform as specific as that. Meanwhile, gravity batteries can be constructed wherever there's enough elevation for the weights to rise and fall. Structures could be custom-made and built from the ground up, or they could be built into pre-built structures, both in use or no longer in use. As long as there's a skyscraper or other tall structure in the area, a gravity battery could be made. Small wonder China is investing so much money into its construction and development. Currently, there are about 6 EVX facilities planned for construction within the country, with capacities ranging from 100 megawatt-hours to 660 megawatt-hours. There are even plans for a facility capable of channeling 2 gigawatt-hours in Inner Mongolia. Combined, the plants cost over $1 billion in capital expenditure alone. To China, it's worth it. The facilities promise a long economic life and require huge amounts of local labor and locally sourced material to build. Said building material is also easy to find compared to the rare metals needed for, say, lithium-ion batteries. All of this combined lowers the facility's levelized cost of storage. The LCOS includes not only the initial capital needed to build the facility but also the costs of operation and maintenance. For example, pump hydro systems have an LCOS of 17 cents per kilowatt-hour. Meanwhile, lithium-ion batteries can have an LCOS of around 25 cents per kilowatt-hour to 35 cents per kilowatt-hour. Compare this to Gravity Vault's projected LCOS for their models at below 5 cents per kilowatt-hour. This makes it surprising and commendable in a way that China is one of the countries leading the charge on adopting gravity battery technology. By 2020, China owned roughly 72% of the lithium-ion battery market. From raw material extraction to the production of battery packs, they have it covered. Their efforts allow for a proof of concept that could give other countries confidence in the technology. This, in turn, would let other countries invest in energy storage in a seemingly simpler, more accessible way, without so much reliance on the Chinese supply chain. An example of this being the Scotland-based Gravitricity. While Energy Vault is focused on building upwards, Gravitricity is looking down. This company caught eyes in 2021 with its demonstration of its gravity energy storage technology. They constructed a 15 tall rig at the port of Leith, Edinburgh, then suspended two 25-ton weights on thick steel cables within. The 250 kilowatts rig was then connected to the grid. It was designed to test how the two weights could smooth the energy output over long periods of time by dropping one after the other, helping the engineers refine the technology.